I've always had a peculiar interest in obscure ways of manufacturing antennas, so today I'm giving you an update on some of the experiments I've been carrying out using machining, 3D printing and electroforming, with a particular focus on the millimetre-wave bands. As we move higher in frequency into the millimetre waves, the required precision of antenna reflectors rises as the wavelength falls. The traditional way of making a parabolic reflector using a spun mandrel and plastic deformation of a metal sheet works reasonably well up to about 30 GHz, but then the errors start to have an impact on the performance of the dish surface. Generally, a surface performs well if the errors are less than about a tenth of a wavelength. At 30 GHz, that means the maximum surface error needs to be less than a millimetre across the entire dish surface. Certainly becomes feasible to machine dishes from solid above about 100 GHz, but if we're looking at 24 and 47 GHz antennas, the required dish sizes start to make it impractical to mill an antenna from solid plate material. A trick I've used is to make the focal length of the parabolic surface much longer than the dish diameter, but that leads to difficulties in illuminating the dish surface efficiently. As we know, in general, it's easiest to illuminate dishes with a ratio of focal length to diameter between about 0.4 and 0.7. Making a dish from a 1-inch thick aluminium plate that's 10 inches square, 250 millimetres, turns a lot of that expensive metal into worthless chips and uses a considerable amount of machining time to remove the unwanted metal. My milling machine has a work volume which is about a 10-inch cube, so it's certainly feasible to make a dish in sections, but making 1 in 4 sections, rather like cake slices, leads to even more material being wasted in order to ensure the dish is sufficiently deep. There is a trick where the surface and rear of the dish are machined at an angle inside the block. That reduces the amount of waste a bit and the thickness of material required. However, it also reduces the maximum diameter. We can use a simple technique to make a much thinner but still effective reflective surface. By combining multiple narrow strips placed along the axis of the dish in multiples of half a wavelength, it's a similar approach to the way a Fresnel lens works, but there's some subtleties that we need to address when the surface is reflecting rather than refracting. If you imagine taking a typical parabolic reflector and slicing it into cylindrical sections and then offsetting each of those sections along the axis, the problem is that each of the rings has now moved along that axis, which means they'll now form a focus at a different point. We can't simply slice up a surface in that way. The trick is to change the curvature of each of those rings so that it focuses at a point which is offset by the same distance that the surface has been moved. As the diameter of the step increases, the focal length of that segment must therefore increase by the same amount. Luckily, there's a relatively simple expression that allows you to calculate the equivalent parabola for that length offset. And if you enter that into a spreadsheet and save it as a comma-separated variable file, you can import it directly into Autodesk Fusion to create a spline curve. That spline can then be used as one side of a thin profile, which then rotate about the axis to create a body of revolution and make a solid surface with the correct profile of each ring. There are some issues around how the curve behaves at each of the steps, but with a sufficiently large number of points, the surface is relatively smooth at the transition. Modelling the transition as vertical steps isn't quite correct anyway, so the fact that a small amount of residual incline is left isn't really that much of an issue. If you think about the shape of the step, a small amount of shadowing would be created if the step was perfectly vertical anyway. There are some machining issues on how you can mill such a surface anyway, because a typical end mill has a flat bottom, even if it's a bullnose with a slightly rounded shoulder. So it isn't possible to machine right to the bottom and right against the face without leaving a trench. My approach has been to use multiple stages of machining and relying on the residual functions within the computer-aided manufacture bit of Fusion to take only the bits that a particular cutter can reach. That means I can use a straight-sided mill to remove the majority of the material, and then a large ball-end mill to create the sloping surface with tiny cusps, which are way less than 1/10 of a wavelength, and then finish the steps using the smaller ball-ended mills. Gives me some curves, but the resulting solid surface ends up with errors of around 10 micrometers. Well, at 47 gigahertz, with a step size of 3 millimeters, that's absolutely tiny and way below the permissible limit. My initial tests indicate that the 240 millimeter diameter step dish like this has a similar performance to a 12-inch spun dish. I need to do a lot more work on it and perhaps look at relieving the rear surface using a honeycomb or some other stiff and light reinforcement pattern that looks shiny and pretty. Now, this dish was made as a symmetrical prime focus reflector, but it's entirely feasible to produce offset dishes using the same approach. If you imagine creating a large parabolic surface and create a conical projection from that onto the surface, as you would if you were creating a normal offset parabolic dish, cutting out the projection of the cone creates an elliptical outline, but so long as it's still large enough to prevent diffraction effects, it behaves exactly like a section of the original parabolic surface. The antenna feed's offset though, so it doesn't block the aperture like a prime focus feed would. The dish is still pretty deep though, so machining it from solid's a bit wasteful. You can calculate the geometry of the multiple curves, each step by a half wavelength, in the same way as we did for the flat plate. The maths behind it gets a little more intricate, but the process is similar. It's just a 3D surface instead of a 2D. However, it's not quite as simple as before to generate the surface within the CAD program. I'm working on a better way to do that to make it easier to manufacture, but it's a bit of a work in progress. These step surfaces also work at frequencies where the step size is a multiple of half wave. So it's possible to make a 24 gigahertz stepped Fresnel sized reflector that also works at 47 gigahertz. Unfortunately, the higher bands aren't very well organised, apart from 122 and 248 perhaps. I've also been working on ways to improve the manufacturing process for making dielectric lenses from solid plastics. Using ultra-high molecular weight polyethylene, UHMP, well, whatever, as the base material of a lens requires maybe a 2-inch thickness of material to make a 10-inch diameter lens. And even then, the focal length is relatively long because of the low refractive index. Materials with a higher refractive index are extremely expensive. It usually involves some sort of dielectric ceramic fill, whereas UHMWPE is a relatively low-cost material which is easy to machine. Ceramic filled plastics sound like a total nightmare for tool life and might also cause, shall we say, issues with the sliding surfaces and bearings within a milling machine. A bit like grinding paste, really. Traditionally, glass optical lenses were made to a spherical profile, but in reality, an ideal homogeneous planar convex lens body needs to be hyperbolic on the curved surface. There's a huge benefit of using lenses at radio frequencies. You don't get chromatic aberration. It's almost entirely irrelevant. It's rather like monochromatic laser lighted lenses. The fact is that the focal point of an optical lens varies with light frequency, and that means that the focus is at different axial positions for different colours of light. And that's been a problem for lens designers of optical lenses forever. The sorts of dielectric materials we're using to make millimetre-wave lenses don't have much of a variation of refractive index with frequency over huge wide ranges. So being able to machine the lenses to a hyperbolic form means that we don't get any spherical aberration either. So all of the rays end up at the same focal point. Solid dielectric plano convex hyperbolic lenses, try saying that after 2 beers, get very large and heavy very rapidly though. So they're not altogether practical even at 47 gigahertz. Brilliant at the higher bands though. Rather than making giant lenses from solid plastics, it's relatively straightforward to make Fresnel style lenses, either by machining or 3D printing. We can't use the thin lens approximation with millimetre-wave lenses though, because they're not very thin, they're kind of thick. And that's a mixture of the short focal lengths and the relatively low refractive index of the materials. The design process is pretty similar to that of that stepped reflector lens, although it doesn't matter so much about the half-wave spacing. So using the same spline generation and body of rotation approach that I did in Excel and Fusion, I can either save the pattern as a step file and import it into my 3D slicer, or I can produce a solid model in Fusion that's ready for CNC machining. With 3D printing, there's a bit of a limitation of the minimum feature size, which means it's rather difficult with a home printer to get much above 24 gigahertz without starting to hit issues about the size of the lattice infill, causing diffraction and other peculiar effects. Machining from solid plastics is a very practical approach, and there are some simple ways to create machine lenses with integrated joints made from the same material as the lens bodies. Things like dowels and perhaps dovetail joints, pretty much like woodworking really. However, gluing UHMWPE, got it again, is an absolute non-starter. It's one of the slipperiest materials around. It's easy to make mechanical joints though to make any larger structures. 3D printing sectional lenses does lead to some interesting challenges though, because it's the dimensional stability and the precision of the faces means that the joints are pretty hard to do. Using high impact polystyrene filaments, one solution, because as well as being a really good dielectric material, you can cement sections together using ordinary polystyrene cement. Remember that from my youth making Airfix models. If additional gaps need filling, you can always just use a bit of the filament. At the moment, I think my Bambu X1C printer may be able to produce viable lenses at 47 gigahertz, but it's right at the limits when I'm using basic cheap filament with low relative dielectric constants. There are some good dielectric filaments around though. mmWave produce a range of filaments with relative permittivity ranging up to about 10. That means you can create lenses that are much thinner than you could from traditional dielectric plastics, but you still got the same problem with feature sizes. And if you're trying to use a gradient index approach, which makes sense with 3D printed lenses, it does mean that you're limited in terms of the highest frequencies. If you're creating lenses like Lüneburgs and Michaelians at home, you have the same constraint over feature sizes, but at 24 gigahertz, a Michaelian is quite a large structure. So it's tricky to get it to fit on the bed and also be sufficiently detailed to get rid of any of these long range effects. Michaelian lenses are very interesting. They've got some attractive features from a mechanical perspective. It's basically just a big flat cylinder. All the lensing is created by varying the density of the print from a maximum at the centre to a very sparse foam or a gyroid lattice towards the edges. The density follows a hyperbolic secant expression, and it's really easy to map that density function onto the wall thickness of a lattice so you can print gradient index lenses. There are other ways of doing it. You can drill a lot of holes and drill more holes at the edge than in the centre, and you can use different materials. So you could make concentric cylinders with different materials or different numbers of holes in. But 3D printing it is nice and easy. You press the button and it just makes it. Okay, sometimes you end up with piles of spaghetti. A Macalian lens works on the same principle as the self-focusing effect of an optical fibre, but if you make it as a flat cylinder that's short enough, it behaves almost exactly the same as a biconvex focusing lens. At least when you look at it from a distance. Internally, weirder things are happening. Let's have a look at what I'm doing with horns now. When you're making a horn at 248 gigahertz, the waveguide diameter is less than 1 millimetre, and the internal size of the horns may be only 3 millimetres in diameter. It sounds that might be tough, but getting the precision needed to machine that with a good enough surface finish to prevent losses from scattering isn't as big a challenge as you'd expect. After all, watchmakers have been making much smaller features for centuries. But making effective horns at millimetre-wave frequencies can also take advantage of some novel manufacturing techniques. If you're making a really tiny horn, but you want to include corrugations to improve the side lobe performance, or you want to have re-entrant curves that are nearly impossible to machine, or complex elliptical or parabolic shapes, machining inside the deep horn starts to become very challenging indeed. Too much stick out. Machining a set of grooves a millimetre or so wide deep inside a horn body leads to all sorts of other problems with chip clearance, recutting of chips, tool chatter, resonances, and then you've got huge issues around deburring once the machining's finished. My current experiments are approaching this inside out. So machining a mandrel from aluminium with the shape being a negative of the finished horn, it's relatively simple to make small features on the outside of a tapered cylinder and then electroplate metal onto the aluminium surface after suitable treatment, and finally dissolve away the aluminium using warm or hot sodium hydroxide, and that leaves behind the electroplated metal. So far, my success rate for that is approximately 0. But now I've got the correct chemicals, I can use the zincate process to put down a conductive layer of zinc, which then I plop straight into the electroplating solution for gold and put a gold layer directly onto the aluminium. Because there's no oxide, having been stripped and then replaced with zinc, the zinc immediately disappears and the gold bonds directly with the surface of the aluminium. So then over the top of that, it's normal to put a nickel barrier layer, but I don't do that. I just do a reasonable amount of gold and then electroform copper directly onto it. But what is happening at the moment is that in the deep grooves, I'm getting inclusions and all sorts of strange things going on, and they're a bit crumbly. So watch this space for news of any progress I actually managed to make. It'll be on the YouTube. I'm trying to use CNC machining to make some non-conical horns with milled axial and radial grooves. The idea being you want to produce a high impedance surface and stop any edge currents. But again, all I've got to show so far is a lot of metal chips and a load of bits and bobs that are in the bin of shame, ready to be melted down and turned into something else. So whether any of these techniques are really practical to make in a home lab and home machine shop is a bit of an open question. There's also issues around weatherproofing, although I'm trying 3D printed radomes now made out of various different dielectric materials. You've got to think about how to keep the insects out. You've got to think about how to keep the weather out. Also, robustness is kind of important, and UV resistance. Making something that works really well but is delicate, as soon as somebody takes it out as a rover or puts it up a mast, it's going to get ruined. For me, the techniques are interesting in themselves though, and it's certainly the case that machined lenses and reflectors are entirely practical apart from the length of time it takes to machine them. Luckily that's my time and I'm not paying somebody else to do it. For me, the real challenge is to make the manufacturing process fast enough to be worthwhile and to produce less waste material. But I'm going back to an ancient technique to help me achieve that goal. My bin of shame is a rich source of small useless pieces of metal which can be melted down and cast into new parts. I can use 3D printed moulds and I can make investment casts using lost foam or lost PLA, or just use traditional sand casting. The cast objects can be made a little bit oversized, so the amount of machining that's needed is minimised, but you get rid of the problem of the outer skin being full of inclusions and not being quite the same as the bulk material. Again, it's very much a work in progress, and I'm currently experimenting with melting small batches of aluminium and copper using an induction heater instead of my big scary propane powered furnace. So far, I haven't managed to find a way of melting down the swarf, the chips, but we're getting there. Anyway, I hope that's given you a bit of a glimpse into some of the manufacturing techniques I've been playing with. I'm having a huge amount of fun with it, even if quite a lot of what I'm creating isn't totally practical and quite often ends up in the bin of shame. Practicality, though, isn't necessarily the key driver. It's the fun that matters.